Good evening, everyone. Welcome to the Washington Quantum Computing Meetup for May 27, 2021, almost post-COVID here in the United States. Anyway, we got a great program tonight, but let me just take a minute to introduce you to some of the events coming up at the meetup real quickly. Oh, by the way, I'm Terrell France from lovely downtown Harrisburg University. Just want to remind you that there are plenty of events on schedule here, thanks to Deb and Helen in their massively impressive efforts in coordinating all these events. We've got on June 12th, Saturday at noon Eastern Time, US. There's a quantum supervised self-supervised learning talk. It's a talk that's going to go over a talk that's or a paper that's on the archive. And in July, there's another event coming up, quantum computing applied to cargo load optimization. So we're getting a little use case oriented here. And in July, the circuit model of quantum computing as if it occurred in an escape room game. This is an interesting talk. I know I've heard the speaker talk about this subject before. Very interesting, particularly if you're interested in teaching quantum computing. But if you're a beginner, it's a real interesting way of thinking about learning quantum computing. Anyway, let's get to tonight. Our speaker, so tonight the topic is, when does reinforcement learning stand out in quantum control? Hopefully we'll hear a little bit about what reinforcement learning is. If you're not a machine learning person, that'll be it's an interesting topic, but I'd like to introduce Asad Raza. Forgive me if I get it wrong there.
No, that was correct, yeah.
Yeah. But he's a math major at City University in Hong Kong, where he also is minoring in physics and computer science. So I'm sure he's got a lot of spare time on his hands. But he's been working in the intersection of quantum and machine learning during his undergraduate work. And presently, I believe he's working on his thesis, a joint thesis of some sort between folks in City University in Hong Kong and SUSTech, which is the Southern University of Science and Technology based in Shenzhen, China. So he's basically heading back and forth across the border there frequently. That area, by the way, if you're not familiar with it, I'm intimately familiar with it because I used to live there. It's known as the Greater Bay Area. Older folks know it as the Pearl River Delta region, but it's probably one of the most fascinating places in the world to live. But it also is one of the epicenters of the future of China, if not the world, when it comes to technology, e-commerce, you name it. It's all the gadgets you get from China basically come from Shenzhen area. But anyway, that aside, so the point is Assad's in the epicenter of some incredible technology. And so welcome, Assad. Appreciate you coming by tonight. And why don't we just turn it over to you?
Yeah, thank you for the very kind introduction. And I think, since we've already talked about, I study math here at City University of Hong Kong, and without wasting a bit of time, I'll ask Xiaoming, my co-author on this paper and a mentor as well, to introduce himself, and then I'll continue with the talk. So Xiaoming, over to you for your introduction, and then we'll move on.
Sorry?
So would you mind introducing yourself for a while, since
okay.
You're
so I'm a PhD student also in City University of Hong Kong. And my major is physics, and working a lot with the reinforcement learning, the application of reinforcement learning and other machine learning techniques in quantum computing. And today's talk is about our recent work about trying to applying the reinforcement learning to the quantum control problems. And we are trying to compare the performance of reinforcement learning and many traditional optimization algorithms and find their difference and potential advantage um, about it. So yeah, I guess you can start.
Great.
Start.
Yeah.
Okay.
So with that, I'll just share my screen and get it going. Sorry, I think. Yeah.
Perfect.
Great.
Yep.
So yeah. So yeah, like Carol alluded earlier, this is a talk where we will talk about the application of reinforcement learning and in a field of quantum control. Now, quantum control has been around for a while. Well, so has been reinforcement learning, but then there was little work that really compared the application of reinforcement learning into this area. Now, there's been a lot of work that machine learning people and also the physics people have done to sort of apply machine learning in different areas of physics. Let's say to astrophysics, to quantum information, and to many other disciplines of physics where people are trying to even discern if there are any new physical laws that they can sort of talk about using these machine learning techniques. So that's the computational physics side, and I think we do something very similar in this paper. And so following will be my outline for the talk. So firstly, I'll talk about the problem statement of the paper, wherein I'll talk about the motivation of this project and what constraints or what conditions do we work on or apply our algorithms to, and then I'll basically give a primer to all the algorithms that we use in this talk, in the work actually, and in particular I'll talk about reinforcement learning algorithms because they are really the cornerstone of our project. Then I'll talk about the control dynamics and constraints of let's say the pulse sequences, and finally the results under various control constraints, and then finally summarize how does actually reinforcement learning stand out in quantum control, which is the question of the paper and the talk. All right, so without further ado, let's just say that quantum control is a wide area, and then basically a simple example of quantum control will be state preparation, right? The state preparation is basically just a task of preparing a desired quantum state. Now, this quantum state is basically a task wherein the goal is to typically steer the qubit from an initial state to the target state, and the mismatch between the final evolved state and the target state that we wanted to reach serves as a natural cost function. So now, in our particular case, for all purposes, we use 0 as the initial state and 1 as the target state, and we basically do the same state preparation from 0 to 1 under different constraints, and then we under different constraints using different algorithms, and then we basically do a comparative analysis of the performance of different algorithms under different constraints to get your state on this block field from 0 to 1. So this is the perfect ideal path that your state will your state will take to go from 0 to 1. So and the cost function, like I talked about, the mismatch is really just captured by the fidelity, which is just an inner product between the evolved state and the final state. Okay. And I'll talk about that further. Like I said, under certain constraints. What do I mean by under certain constraints? Well, basically, what we do is that, like I alluded to earlier, we have these 5 different algorithms that we do a comparative analysis of under different controlled field strengths, let's say, and those will be our primary constraints for the state preparation problem. So for the rest of the talk, that is the problem that we're working on and trying to solve. Okay, so that being established, pardon me, we can talk about just the primer to these algorithms that we've used, right? So the first one is a stochastic gradient descent algorithm, which is just the good old gradient descent algorithm that samples points stochastically, very widely used in the whole of machine learning, classical machine learning, even quantum machine learning literature. That is a first order algorithm. And in particular, that what it does in our case is that it updates the control field using the gradient of the fidelity cost function, right? And so the second algorithm would be that we evaluate is the Krutov algorithm. Now, this one has been around for a while, and to my knowledge, this has been very useful in classical control as well, to the point that it helped some of the early advances in I guess I'm not sure about this. I guess it was the early flights that we took. So so what happens in Krutov is that you have the initial state, and then the initial state is first propagated forward, obtaining the evolved state, and then the evolved state is then projected to the target state that we wanted to go to actually, right? Now, this defines a co-state which encapsulate really the mismatch between the two. And then the co-state is finally projected backwards to the initial state that we started with, during which process the control fields are essentially updated. And then we have 3 reinforcement learning algorithms, which are really the cornerstone of the project. So number 1 is the tabular Q-learning. So the tabular Q-learning is basically a reinforcement learning algorithm. It is like how humans learn. You try something, or actually all of reinforcement learning is like how humans learn. So it's essentially you have an agent. So let's say that as a human being, you're an agent in this universe, and then you do certain things. When you perform a certain action, you see that a certain action gives you some sort of happiness or pain, and then you try to avoid pain, and you maximize the things that increase your happiness or eudaimonia, if that's too philosophical. So yeah, we humans work based on rewards, right? And so basically a similar thing is a basic working principle of reinforcement learning. In reinforcement learning, we have an agent that takes certain actions, and then based on those actions, you land onto certain states. And when you take a certain action, you get a certain reward. Now that reward may be positive or it may be negative. So you get penalized sometimes, and sometimes you get rewarded for whatever action you take. And depending on the action you take, you go into a certain other state. So in tabular Q-learning, there is a table of states and actions. That's in my next slide, and you basically are traversing that table for the ideal reward value in that table. Now, the deep Q-learning is basically the same as a Q table, except that as tabular Q-learning, except that Q table is replaced by a neural network. So I'll talk about these 2 again in the next slide. So don't worry if that was too foreign. And then finally, we have PG, which is policy gradient. Again, a reinforcement learning algorithm, wherein the network outputs the probability of choosing each action. So it's more of a probabilistic type. So here, so the TQL and DQL are sort of important algorithms here. So how it works, like I said, you have a table. So like this is the left one is TQL and the right one is DQL. So for tabular Q-learning, you have your states and actions. So this is like a matrix you can imagine. And let's say that you're on the state S5. Now what you'll do is that you'll see that being in a row of state 5, what action can I take from A1 to AN, let's say, that will maximize my reward. So we are assuming that A3 was the one that maximized my reward, right? So I will take action number 3. Now taking action number 3 will take me from my initial state, that was state 5, to state 2, let's say, right? And once I take that action, I will update. I'll basically update my reward table according to the following equation. So for DQL, what happens is that instead of this Q table, you have a neural network, right? And when you have a neural network, you basically have state amplitudes or your quantum state amplitudes as inputs, and then you get outputs, and then you get actions as your outputs. Now, the fact that you can input state amplitudes really allow you to input continuous states, which is just to mean like superposition of states, right? So, however, in here, in tabular Q-learning, S1, S2, S3, you could just input like a discrete state. So that is a possible advantage of DQL over the tabular Q-learning. So so that was a quick introduction to both tabular Q-learning and DQ-learning, and then how do we apply these two algorithms or reinforcement learning in general to our setting, which is a quantum setting, so to speak. So like we talked about, we have states, actions, and rewards. That is sort of the principal working idea of reinforcement learning. So in our case, we can map states to quantum states very naturally. And then actions are basically Hamiltonian operations. So what is a Hamiltonian? I'll again talk about that in detail in my next few slides. But then Hamiltonian, you could really talk about. You could really think of it as a sailor of your boat, which is your state, right? And then the Hamiltonian is a captain of that yacht, which is your state, and then Hamiltonian will drive your state to wherever you're taking it. So
I asked that.
Yeah,
I'm
sure.
sorry. So do you want to answer the questions now or after your talk?
I think let's do it afterwards.
Okay. So please continue.
Yeah. So also Xiaoming, since you're a co-author, so feel free to chime in if you feel there's anything you need to add. So
Okay.
yeah, feel free. So yeah, and then the Hamiltonian operations will really drive the quantum system. And finally, when you apply a Hamiltonian operation, your state goes from let's say initial state to the next possible state. And when you go to another possible state, you will have a reward of that may be positive or negative again, and then you will see that given a particular state, when you take an action, what is the reward that I get, and based on that reward, I will have a probability of choosing each action at a particular state X S. That is my policy. Let's say in the policy gradient methods. Okay. So yeah, that is how we map the problem. We map the reinforcement learning from the classical or the traditional sense for a particular problem. Okay. That being said, we can further talk about now the dynamics of control. So like I promised, that I'll talk about the what a Hamiltonian is and what we're working with here. So so here, this equation really encapsulates our Hamiltonian that we work with, right? So Hamiltonian, like I said, can be intuitively understood as like a captain on your yacht, which is driving your state. And so here, your Hamiltonian is dependent on JT, which is the control field, right? And the control field can be thought of as a pulse sequence or in a practical setting in a lab, right? So I think that is the most intuitive, practical, like sort of not analogy, actually, example of a control field. So so that you have a control field, and then you have the Hamiltonian that depends on this control field strength. What you do is that this Hamiltonian is basically looking like this, where you have psi z and psi x, which are fixed, which are Pauli z and Pauli x matrices. On the other hand, you have H, which encapsulates the energy gap under tunable controls. Now, in these systems, it is difficult to vary H, during gate operations, and we therefore assume that H is a constant in our work, which at the same time serves as our energy unit. So, given that all of the Hamiltonian is constant, there's only one thing that we need to tune for a training, and that is JT, which is control field, right? So we isolate the control field and work on it, and make predictions about, not make a comparative analysis about various algorithms. So the task here is that we have to find JT such that the fidelity between the initial state, which was 0 in our case, and the final state, which was 1 in our case, is as high as possible in time t equals to 2 pi. So now we fix the time of the evolution time to be t equals to 2 pi for uniformity of and in order to compare all the algorithms fairly, we fix the time, and so we see where the fidelity is the highest, or which algorithms or algorithm performed the best. Okay. Now, the assumption that we make here is that we say that the control is performed by n piecewise constant pulses. So the control is basically a piecewise function where you have like n piecewise constant pulses in a time t equals to 2 pi. So for a small time dt, you will have t over n duration of the pulse. T over n duration of the pulse. So by that, on ith step, the JT is given as Ji, which is the control field as at ith step, and the state psi I at any given step, ith step, is basically just a unitary evolution from I-1 state to the ith state, right? And what does this unitary evolution look like? Well, the unitary evolution is very simple. It's just the exponential of minus I times the Hamiltonian, which is how most unitaries are represented, and so that would be the unitary evolution from state I-1 to state I using this e to the minus I h dt. So that is the dynamic of our control, and like I said, the task, circling back, is to maximize the fidelity between 0 and 1. So since that was a task, the results of the different algorithms are as follows. So so this is really the encapsulation of all the results using different algorithms. So n is basically the number of discrete control pulses, right, in a pulse sequence. And so on the x-axis, on the y-axis, we have the fidelity, the average fidelity. So let's say that I perform a routine one time, but then obviously for statistical accuracy and statistical due diligence, so to speak, you definitely have to average it over a certain run. So we average it over, I suppose, 500 runs, if I remember correctly, or 100 runs, something along those lines. So yeah, but I think, yeah, the number is not too important. The fact that we iterated or averaged over enough number of times really tell us that we're not, that we're doing, we are scientifically okay, or statistically okay. So yeah, the y-axis is the average fidelity, and fidelity obviously is an inner product. Absolute value of the inner product will take values between 0 and 1 and inclusive, and no more, no less. So yeah, Now, the results basically suggest something interesting. We see that the policy gradient method consistently outperforms almost all of their methods. Deep Q learning is also not too bad. However, we see that as n increases, stochastic gradient descent really is performing really bad. And one might wonder what would be the reason for that. Well, the reason for that is that we have fixed the number of gradient updates or the number of epochs, if you may, in the stochastic gradient descent algorithm, right? Which is, I suppose, 500, just to make the analysis between SGD and Krutov equal, because Krutov also requires a fixed number of initial steps. So just to fix that number and make the comparison uniform, we fix that initial number of steps. But now what is happening is that the updates to gradient to stochastic gradient descent are fixed. However, the problem is becoming more and more complex as this n is increasing, because now your search space is sort of larger and larger, right? You have more discrete points at which you have control pulses. So so then it really becomes more and more difficult for SGD to optimize for the same number of steps, but for a larger parameter space. So for a larger parameter space, SGD would require more steps, but then since it's fixed, it's difficult for SGD to maintain consistent performance. So that is the most plausible reason that SGD performs SGD's performance deteriorates with increasing n. And then we see that among all 5 algorithms, policy gradient is consistently the best. Apart from policy gradient, deep Q learning gives the highest fidelity for n is less than 30. However, there's always a non-zero failure probability, and because of that, it is not really visible in the graph perhaps, but it's slightly outperformed by Krutov for n equals to 30, but that's on the 3rd decimal place, so the fidelity was like 0.998 versus 0.999, I suppose. So that's not too big of a difference to care about. The thing to note here is that the reinforcement learning algorithms, both of them, DQL and policy gradient, are performing really well. However, one might wonder that if reinforcement learning algorithms are performing so well, then why is the TQL, which is a tabular Q learning, going down? Like the fidelity of TQL is going down as an increase. So also note that TQL is using a Q table, which is discrete. And as you're increasing n, you're increasing the size of the Q table, thus the search space for the Q table, right? And when you increase the search space for the Q table, it becomes more and more difficult for TQL to keep up with the performance. All right. So that being said, we look at, we further evaluate the previous results. Pardon me. We further evaluate the previous results using by looking at the pulse profiles of let's say a random path sequence. Right. So on the y-axis, you have at the ith step you'll have the pulse sequence ji, and so we see that the diagram A, where you have A and B, where you have SGD, you will see a pulse sequence that is the final optimized pulse sequence that takes the following path from 0 to 1, which is rather complicated. On the right, C and D figures are showing how the Krutov takes the path from 0 to 1. So now I should also mention that J here is bounded between 0 and 1 and can take any value between 0 and 1. So yeah, that's why it's the y-axis show that point for SGD. However, for TQL and DQL, since TQL is it can only take discrete states and discrete actions, JI could only take values 0 and 0 or 1, right? But then the pulse profile for TQL, DQL, and PG, the reinforcement learning algorithms, in short, look very interesting, to say the least, because it's just that you just switch off JI for or 0 JI for t equals to t by 2, like the time period by 2 for half the time period, and then you are through. Now there is also an intuitive reason for that, and that is because if you look at the Hamiltonian has the following form. Now imagine if J is 0, all you have is a poly X term, right? And the poly X term is basically the term that will lead you from 0 to a 1 and 1 to a 0. So in our case, for going from a 0 to a 1, in the quickest way possible, you will just turn off the JT term, and you're, boom, you're there. And so it really figures out the optimal path to the desired target state of 1. Now, there's also one more important point that one should note here, that now these reinforcement learning algorithms altogether do not have an initial number of fixed steps, right? So like for SGD, you have to complete all the steps, and the same for Kratov. Now, in that process, you might overshoot the minimum, such that by overshooting, I mean that, let's say that you're close to the minimum, let's say that at 20th step, you're close to the minimum, but now you have to complete all the 30 steps, right? And because of that constraint of completion, you might just go away from the global minimum if you are there. However, for TQL, DQL, and policy gradient, it's not that constraint is not really there, because as soon as you converge to the perfect reward function, or to the perfect reward, you just basically stop, and that is why we see that just in half the steps we have really achieved the optimum performance, as good as it could be. Like I showed in the initial slide, the GIF that went from the animation that went from 0 to 1. In that direction. So that's the pulse profile. But now we make it a bit more interesting, and we work with a different scenario. So like I alluded to in my initial few slides, that we have different constraints, and then we analyze the performance of these algorithms and different constraints. So this is a different scenario. Like this is I would say a slightly complicated scenario, where you have where you just don't have the bounded control fields. You also have only m plus 1, let's say m, right? Let's say m allowed values of the control field, right? So here, if you look at the pulse profile, this ji could take any value, right? Although it's bounded between 0 and 1, it could take any value, right? But here, it's not just bounded. It's also required to take discrete values. So I would say that ji could only take values 0, 0.2, 0.4, 6, and 8, and 1, nothing else. So whenever you're at a point, you will really just round up or down depending on the closeness. So when you have these discrete control field, where you have just m allowed values, here is an interesting case. So the figure A is basically where you have n equals to 6, which is like the pulse, which is the number of pulse divisions, and then the second one, the figure B, but right below it, is basically where n is equal to 20. So the first figure has a smaller search space, and then the bottom figure has a larger search space. So we see, now what we see here, is that for from first to the second figure, the performance of stochastic gradient descent goes worse, right? And why is that? And goes worse with n and m. With m, it stays perhaps the same, but then with n, it goes worse. And why is that so? Well, again, because the search space is just too large. However, we get an important insight by doing this sort of constraint arrangement or discrete arrangement, and that is that we get to learn that the reinforcement learning algorithms, which is DQL and policy gradient in particular, they perform well. DQL and the policy gradient algorithms, they perform well when the problem is discrete, right? So we see that for smaller m, they have much higher fidelity. That is almost close to the unity, which is the best you could get, right? Which is very close to 1, like very close. So so what we learn here is that reinforcement learning algorithms are amazingly good with the discrete problems. And again, that is because when the problem becomes more and more continuous, then what happens is that the size of the Q table increases, the size of the neural network increases, or neural network becomes complex, or its representation power has to be improved in order to make better predictions about the continuous landscape. However, if it's discrete, it's super easy. I'm not super easy, but then it's the size of the search space is rather small, and so these techniques, DQL and the DQ learning and policy gradient methods can do really well. So we see that this behavior is replicated in both n equals to 6 case, which is the top feeder here, and then n equals to the 20 case. All right, so the note, I think I alluded to that earlier as well, and explained that as well, that the average fidelity to the 3 reinforcement learning algorithm decreases with n, albeit not considerably. This is because obviously that TQL and DQL favor bounded and concrete sets of actions, and more choices will only add burden to the searching process, rendering the algorithms inefficient. Okay, but then again, like I talked about, improvements could be made by increasing the number of iterations that we did in a separate supplementary section in the paper, or using a larger neural network that has a strong representational capacity. So yeah, these are perhaps some of the ways you could work around to make the performance better. Okay, well, in summary, what we see is that RL, so reinforcement learning, works really well in discrete settings, and stochastic gradient descent is more inclined towards discrete, towards continuous ones, right? And secondly, the second most important finding is that performance of SGD and the reinforcement learning algorithms deteriorates with increasing n. So we see that performance of all the algorithms, let it be stochastic gradient descent, tabular Q learning, DQ learning, it will deteriorate with increasing n, with the number of pulse divisions, and that is very intuitive, because if you increase n, you're just increasing the parameter search space, and then you just have to search more and more and more and more. But what is surprising, or what is at least not intuitive to, let's say, a practitioner, is that with increasing search space, SGD will deteriorate far more quickly than these reinforcement learning algorithms. Now, this is, I believe, this is not a universal truth, definitely. This is rather application dependent, and that is what makes our results interesting, is that in our application, which is an application to quantum control and state preparation in particular, we see that with increasing n, it is far more sagacious to use reinforcement learning algorithms, because even if you increase the pulse divisions, that is increase n, you will not give a cost as high if you were to use stochastic gradient descent. All right, with that, I will finish the talk and open the floor for questions. Thank you for listening.
Okay, thank you for Azad. So can we take questions now?
Definitely, yeah.
Okay, so I guess you have already answered the question, what are SGD, TQL, and DQL, and what are the advantage and disadvantage of those algorithms, which has been summarized previously. And there are some other minor questions. What defines value of the rewards, and is value a fixed target or a variable? And is the rewards matrix fluid? So basically, maybe I can answer this kind of question. So basically, it is a value which has a function of the preparation fidelities. So it may not be exactly the value of fidelity, but as a function of it. So like your current state is more close to the target state, your reward will be higher. And that's how the reinforcement learning work, I guess. And the next question. So if t equals to 2 pi, how can time be fixed when p is irrational and yes, transcendental? I guess yeah, that's a question. So actually, when you do experiments on numerical simulations, there should be an accuracy of uh, the the time. So maybe you need to approximate 2 pi kind of. So in quantum control, you never have an ideal power sequence. You will have some errors from many aspects, and the truncation of uh, the numbers, the accuracy of pi kind of that is one of them. Yeah.
So I think just to add to that, thank you, Xiaoming, for answering the question. Just to add to what Xiaoming said, for t equals to 2 pi, I think the classical computers that we use, to make perhaps to research better quantum computers. These classical computers have an accuracy of 64-bit floating point numbers, like 64-bit floating point representation, let's say. And so you could only represent so much of the digits. So I think as long as you're close to 2 pi, even if you fix it to 6 point something, that should be all right. So I mean, that is about approximations, but that is not too big of an issue. Once you fix any number, until any particular decimal accuracy, you can move on with your experiments.
Yeah, I guess so.
Why XYZ plot coordinates are left-handed? So Xiaoming, I'll keep it to you to read the questions, and then we can answer to you.
Yeah. So why XYZ plots coordinates are left-handed? So usually it should be right-handed, but I guess we change the axis in order to make the trajectory more clear. So because as you can see, it is kind of the trajectory is kind of facing you now. So if you use a conventional coordinates, I guess it is less clear. So yeah, so maybe this is the reasons. So actually these figures are plotted by the second authors of this paper. So yeah, so this is my understanding of the figure.
I think you could only just rotate this in Matplotlib using the interactive function. I forgot the function called to it. So you can really plot a 3D image, and then you can rotate however you want in the 3D space in your computer, and then you can select the orientation that suits your representation best.
Yeah.
So
until it is most clear.
And anyway, these coordinates are just arbitrary, right? So you can pick X as the vertical axis as long as you find it convenient.
Yeah. Thank you for the questions. And any way to improve the performance of those algorithms? I guess you have answered part of these questions previously. So for the reinforcement learning, so you may use a larger neural network and use better training methods, and this is actually an ongoing ongoing fields with many new methods are emerging every days, every week, something like that. So yeah, I think this is a very interesting question.
And also you might use better initialization. So here, so for JI, we start with a particular random pulse, and then we update the values of this pulse sequence using the gradient updates, right? But let's say that you're in a cost landscape, I start close to the local minimum, and then you start very high up on a cliff on the landscape, let's say. So for me, it's easier to find the global minimum than for anyone who starts at a higher cost value or a higher loss value, right? So better initialization can help you. Is another way to help you with the improved performance.
Yeah. And okay. And for the next question, are these dynamically? So thank you for answer on target states. Are these dynamically variables? How do these deal with the error in the estimates of t equals to 2 pi?
So I think that, like I said, as long as you fix a value for t equals to 2 pi, right? So that after that, you can just work on with using all the algorithms for that particular time, that particular constant value of time. So even if
I guess there is a slightly difference between the methods for SGD and Krotov and the reinforcement learning, right?
right,
So,
but then for both of them, we use time t equals to 2 pi, but then one converges quickly and one converges late, right?
Yeah. And I guess in the first two algorithms, you update exactly the fidelity at steps in this figure steps 20. Right? So you are updating the pulse sequence in order to update the final fidelity. So, but in the reinforcement learning, it is a little bit different. It will evaluate the fidelity at every steps, and it will have its own kind of predictions or estimation on the final fidelity. So final does not necessarily be the values at the step 20. So it can stop wherever it think it is good enough. It's something like that. So actually the algorithm is very tricky. Right? So I hope we have answered your questions.
And also just to add to what Xiaoming said, if you're concerned about why t is just equal to 2 pi and 2 pi is irrational and so on, again, the point is to fix a time period for all the algorithms. Right now, they can choose to converge quick or faster depending on their principle of working. If you like, you can choose t to be, let's say, not an irrational number. You can choose t to be anything.
Yeah.
Right? You just choose t to be 2, right? Doesn't matter. And but then 2 pi is chosen because it's the period for most functions that are of interest. Right? So like the sinusoidal functions, and so this comes up every now and then. It's a standard scientific practice to do that. But if you like, you could do that by just choosing t equals to 2 or 3 or 5, 10, whatever you like.
Yeah. What do you think might be an application of these techniques in real worlds? I think this is a very interesting question.
Before we move on, I just got a very interesting point for the previous question as well. So if you have like a periodic sort of an optimization and you choose, let's say t equals to 12, right? All you will see is that your values will be repeated like, let's say, twice, because you are doing one thing for one time period and then if the period is 2 pi, you take it to be 12, then it's like repeated 4 times. If it's 6, then 6 point something, then repeated about 2 times. So it depends on, if you're working with periodic functions, you will see like some repeated patterns depending on how many periods you take. Okay. So yeah, that is also one thing to look out for, perhaps, if you're interested.
Yeah. So the next questions, what do you think might be an application of these techniques in real world? So Asas, do you have any
Sure, I
idea?
think that's an interesting question. So one application I think might be let's say in quantum machine learning, right? Quantum machine learning deals with starting from an initial state and going to a target state. So so in there, you have a unitary. So now this is a rather loose example I can see, but then still, an easy way to visualize it is that you have the initial state can be thought of as your starting point, and your target state is a label. So let's say, let me give an example. So if you have a picture of a cat and a dog, right, and you want to identify whether it's a cat or a dog, what you will do is that you'll start from something and then you go to some final state, and then you compare the fidelity of that final state with the state that represents the cat or a dog, right? So it's in a sense a state preparation problem, right? So when you compare that fidelity, you'll see that whether you're more closer to the cat or the dog. So whichever fidelity is higher, you will say that, okay, I start from that particular state, but then it seems that the fidelity with the cat at the end of the routine is fidelity with respect to the cat, the state that represents the cat, because there's also a cat state in quantum mechanics. So the state that represents the cat is higher than the fidelity of my final state that is, so the state, sorry. Let me compose myself. So I start with some state, I go to the end, I get the final state.
Protocolo que já, o negócio já começou a ser feito de novo.
So I go to the final state, and then I basically just compare the fidelity. If the fidelity of the cat is higher, then I'll say it's a cat. If the one with the dog is higher, I will say this is like a dog, let's say. So that is one thing. But then I think it has a lot more applications in quantum in the physics aspects of things as well. I'm not sure if Xiaoming has anything to add on the applications part.
I think so. First of all, reinforcement learning itself already found its applications in many interesting fields, not in quantum computing. So you know, something like AlphaGo and the DeepMind company have developed many interesting applications. Yeah, to my understanding, one of it is in the playing chess, game of Go, and some other applications like playing games like Dota and hide and seek. Some interesting game playing tasks. Yes, I guess this is the state of the art applications, and in quantum computing, actually, people still exploring these fields. So one of the possible application is, as Azar says, the state preparation. It is a very general and very fundamental problem in quantum computing. So we are just discussing a very simple examples. But if the problem is has a larger scale, so maybe the prepared state is more meaningful. So in that case, maybe the reinforcement learning has its applications. So I guess this is a very interesting questions, and it's still an ongoing work in the fields, right? And yeah, there's another question. So do you think machine learning can be used to reduce error that occurs in qubits? So actually, I think this could be one of the applications, although we haven't tested for it detailedly. And actually, there are some other works about applying reinforcement learning to quantum error corrections. And some of the researchers have found some interesting results. So I think this is actually possible. Yeah.
I think, Xiaoming, you have a paper recently that explores
But
um,
yeah,
the same idea, right?
yeah, that's not
Similar idea.
with reinforcement learning, but with machine learning, the unsupervised learning.
Yeah, yeah.
I guess the goal is similar to reduce the errors in quantum computing. Nice. Yeah. Yeah. Thank you for the questions.
Okay, well, let me wrap it up here then, if I may. Assad and Xiaoming, thank you very much.
Thank you.
Thanks everybody for coming out tonight, and we'll be looking forward to the next paper that your team, the pair of you and others put together. So I'm sure, if I can speak for Deb and Helen, I'd like to invite you back once you get that next publication out there. Keep up the good work.
Sure. Be glad to come back again. Yeah, definitely.
Cool.
Thank you for the invitation.
Cool. Always welcome.
Yeah.
All right, folks. I put the link to the next event from Washington Meetup in the chat there. So everybody have a good evening and good day coming up. So thank you very much.
Thank you.
Thank
for
you.
joining.
Yeah.
Right. Yeah. Bye.
See you. Bye.